So welcome to today's seminar. Okay, our speaker today is Rony Granek, okay, from Ben Gurion University of the Negev. Okay. I have a story about my mispronunciations, but I'm not giving it. Okay, later. Okay. Dr. Granek is a full professor in the Department of Biotechnical Engineering and an adjunct professor in the Department of Physics. He received his PhD in chemical physics from Tel Aviv in 1990. His interests include biophysics, soft matter physics, statistical physics, and mathematical modeling. Rony is visiting us for 2 months. Okay, actually, he's here to work with Pete Vahuska on membrane problems, that's my understanding. Okay.
Yes.
And so his office is down the hall. And so anybody wants to talk to him over the next 2 months, I'm sure his
Month
door.
and a half now.
Okay. His door is open. Today, he'll tell us about work on active fractal networks with stochastic force monopoles and force dipoles unravel subdiffusion of chromosomal loci.
Thank you very much, and thank you for having me. So I guess you can read the second line here. The first line is in Hebrew, and that's the sign of my university. And in fact, today is Israel Independence Day, so it's a special day to give a talk. So this is my main affiliation at the biotechnology department, but I'm also adjunct at physics, and I'm a member of the Nanotech Institute. The work was done together with my postdoctorand from India, from Varanasi, Sadhana Singh. It's still in the archive, not out yet in publication, and I'll begin, therefore. So let me give you some introduction. So intracellular environment of living cells is rich in active force fluctuations. These forces are generated by molecular motors to maintain the biological activity of the cell. Molecular motors convert chemical energy stored in ATP to mechanical energy, which results in active non-thermal force fluctuations that can dominate over thermal fluctuation. So, of course, these forces are for transport or to actually use a certain force to create something, to do something, but there is noise in this force, and then it creates active noise, what we call active noise. So in a variety of experiments, the random diffusive motion is found to be anomalous, where the mean square displacement, what we call MSD in short, obeys a scaling law where the MSD is the scaling like T to some power nu, and nu may not be 1 like in diffusive motion. So I wanted to mention a certain experiment was done a few years ago on E. coli cells and yeast cells. And basically what they showed is that locus dynamics in live bacteria and yeast are sensitive to metabolic activity. When ATP synthesis is inhibited, the apparent diffusion coefficient, actually it's the free factor instead in front of the scaling, decreases, whereas the subdiffusive scaling exponent remains constant. So they conclude that indeed untreated cells, normal cells, have an additional source of molecular agitation beyond thermal motion. And such ATP-dependent fluctuations are likely to be mechanical. And in summary, that's the results. So what you see, the bottom blue is the ATP depletion. The red is normal cells. It's log-log MSD versus time. And this is the scaling they found. And both the untreated and untreated normal cells and treated is ATP depleted cells have the same exponent. And okay, there is some kind of distribution of exponents, a small one, but this is quite robust, relatively robust for a biological system, although it's something between 1 or 2 and 2 orders of magnitude, so you can question this. Now, from another source of information came from mammalian cells, and this is from Israel. Yuval Garini and co-worker, now in the Technion, but he was at Bar-Ilan University at that time. So he looked at telomere motion in mammalian cells and basically found that, he found anomalous diffusion. The exponent, this is now divided by time. This is why it's decreasing because it's t to the nu minus 1 here. In fact, this I took from his supporting, maybe what he said is not sure completely about that, but actually for ATP depletion, there was a slightly different exponent, so maybe it's not so general, or it was some issue with the experiment. Anyhow, it's different cells. So biology is like that. You have to accept. So how do you get forces in cells? This is just an example of many molecular motors, like the actin-myosin system. So these are muscles act with this, and any actually cytoskeleton in any cell is an actomyosin system. So you actually pull or push actin fibers. So why did I say this is surprising? Two exponents, one ATP depletion and one normal, same exponent. Why do I say? Because I know something about these systems. And what I've done in the past is use a generalized Langevin equation, like just a single particle, where all the viscoelasticity, if you like, the strange thing about the system comes into the memory kernel here. And this is the high damping limit. So there is thermal noise and there is active noise here. Thermal noise obeys fluctuation dissipation theory, but and that means actually when you translate this to the thermal MSD, there is a relation between this memory kernel in Laplace space and the MSD in Laplace space.
I don't understand that first question. There's no integral, is that over T prime, but there is the dx.
There is a T prime.
Right, but it looks as if you push us through the integral, it's such a constant.
It's a dt prime, I'm sorry.
So it should be x of T prime, d by dt prime.
Yeah, dt prime, sorry. I forgot this.
Okay,
Yeah, I'm sorry.
okay, that makes more sense.
No, it should make sense. Yeah, you're right. Sorry about that. Anyhow, so you see, you go to Laplace, you have a kernel, so it's easy to solve, and that's the relation between MSD in S space and this memory in S space. This is called the generalized Einstein relation, which follows from fluctuation dissipation theory. Now let us define the Laplace transform of. Okay, so using this mu s, 1 over s mu s is actually the Laplace transform of something which I call mu e of t, just for the convenience. And basically, that mu e of t obeys also this relation in a time domain where this should be small th thermal. Okay, again, small mistake again, and sorry about that. And therefore, so if the MSD, the thermal MSD goes with a certain exponent nu thermal, then mu e is going like t to 1 minus nu thermal. And then for active force contribution, you have this double integral. We just integrate the Langevin equation here. And you forget about this now, you only use this. And let's take this kind of exponential correlation function for the active force. So at long times, it's actually effectively delta function. And so for a long time, it's easy to know what happens. So what happens is that you find anomalous diffusion at long time, subdiffusion. The exponent has this relation. So nu active is 2 nu thermal minus 1. So definitely they are not equal unless nu is 1. If it was a regular diffusion, they are equal. So 2 minus 1 is 1. So and if nu thermal is smaller than 1/2, it just saturates it. You don't see anything. At short times, you have ballistic motion. Okay, or you have superdiffusion in general, not ballistic, superdiffusion. So this cannot explain the experimental results. That's why that's something that the naive way of explaining things doesn't work. But in the past, it worked, like with the group of Michael Elbaum, we tried to explain how a bead that experienced phagocytosis is moving inside the cell. So you can follow it and you see stationary noise. You can calculate MSD using time averaging. And what we find, so for passive system, there was T through 3/4, which could explain by the properties of the filaments, in this case, the microtubules, plasticity of microtubules. And the active system was short times superdiffusion, T to the 3/2. We could also explain this. And the long time active, that's roughly the correlation time of this force, then it was T to the 1/2, as you would expect from this relation. So somehow me and other people in the field, like Fred McIntosh and collaborating with Dave Weitz, actually thought this is quite general, and you don't have to work out to understand the system. If you know something about the passive system, you know the MSD, then you can derive the friction, the time-dependent or frequency-dependent friction, and then you can know what's going on for the active system. But it doesn't work here, and the reason it doesn't work here is because actually I will say that chromatin has a lot to do with fractals, so I will say it in a moment, but let me give you some introduction to fractals. Although this is an applied math, so I guess many people know. So the idea of fractals is, let's say if you look at mass enclosed in concentric spheres of increasing radius, so if it's the distribution of mass is uniform, that in 3D, it should go like R to the 3, number of the mass or the number of particles. In Euclidean dimensions, R to the D. And if there is a DF there, then it's called the fractal dimension or the Hausdorff dimension. But there are other dimensions, like the topological manifold dimension, which is the one really dimension defined in the manifold. The easiest example is to think of a polymer that is folded. It's a manifold dimension, or topological dimension is always 1, but the way it folds will determine its fractal dimension. So if it is a Gaussian chain, its fractal dimension will be 2. If it's a self-avoiding chain, its fractal dimension will be 5/3, 1 over the flow. And if you don't know, you can, for example, measure it if you look at the chemical length. The scaling between L and R is defined the chemical length dimension. So you're looking for the shortest path along the manifold between 2 points. This is L. And once you have this D mean, then this is the relation between DL and DF. Now, okay, it's decades of work and this kind of stuff. The other thing I want to tell you about is the density of vibrational states. So you suppose the fractal is made of beads and springs. So, and let's assume pure vibration. So there are normal modes, okay? And you can calculate the density of these normal modes, the eigenstates. And if the scaling is like that, then omega to the ds minus 1, this is called the spectral dimension. For Euclidean dimension, ds is again the Euclidean dimension. So, and then it's called the bi density of state that you learn in maybe second year course in physics. I mean, just solid state physics, it's like omega squared, right? So, and there is this inequality between dimensions. It's again well known, but I'm telling you because otherwise you won't be able to understand what I'm saying. So again, a part of the introduction is we look at vibrations on a fractal. You can have it with an equilibrium distance of the springs. M omega 0 square is actually the spring constant, just written with the spring self-frequency. And you can move from distances to displacement the usual way. Our zeros are the equilibrium positions. But only for B equal to 0, you get scalar elasticity. For B non-zero, it's an approximation. This is called scalar elasticity Hamiltonian in the jargon. If not, so if B non-zero, it's an approximation and it may fail. But analytically, what I'll show analytically, we were using only scalar elasticity because we are not strong enough in mathematics, unlike you. But numerically, we also use B non-zero. I mean simulations. So what are, if you wouldn't have friction, these are the equations of motion for vibrations in the network. You have a certain network, whatever the network, it doesn't have to be a fractal. We look for the normal modes, as you know, and the normal modes obey this kind of thing. And this sign is those nodes I that are J that are connected to I. Okay, so basically you go for here, you go on all these neighbors in topological space, nearest neighbors in topological space, not in real space necessarily. You can also think of the calculate from this the density of states, as I told you about, or the cumulative dose, which is the integral, the number of states until a frequency omega. And this has been done. These eigenstates on a fractal are called fractons. They are localized, strongly localized. So you see, instead of having a wave, a sound wave, see these amplitudes are localized. This is a percolation cluster in 2D. And you find this scaling. And in addition, there is an interesting thing. Maybe I shouldn't say so much about it. It's called Landau-Peierls instability. That is, for ds smaller than 2, you get a divergence of the thermal MSD. This was measured, for example, by these people, Jakubo, etc., Orbach, a long time ago, very, very long time ago. And you see at the percolation threshold, you are fractal. If you are away from the percolation threshold, you have also you have this Debye behavior in 2D is omega. And this is the known spectral dimension in 2D. Okay, and actually, some time ago, we found that even proteins are fractal-like, but I'm just giving you publicity for these papers. I mean, so some things are fractal. Sometimes fractal is always approximation, but it's nice to work on. And so it gives you a guideline for something. So why fractals at all? What's the relation between chromatin dynamics and fractal? Okay, so some time ago, actually, I think 20 years ago, or more than 20 years ago, so Alexander Gosberg and co-workers initiated what is called the fractal globule model, where actually it's not fractal in terms of the fractal dimension, because the fractal dimension is strict. So it's space filling, but still it's based on a single chain crumpled. And as I told you, it's not a simple kind of configuration, because let's say Gaussian chain fractal dimension is 2. So we have to do something to get it. These are, for example, these are actually chromosome territories, these colors, but this kind of sketch of a spatial filling curve. And what you see, for example, it has certain properties like contact probability, the probability that a segment of length S will come back and be near this segment. Okay, so let's say this is the origin, just a segment, just arbitrary origin, and this probability goes like S to the minus 1, and not like, for example, S to the minus 3/2, which would be the case for Gaussian chain. And that's related, it's because of this scaling. In practice, the model is not perfect. So in fact, the fractal dimension is 2.7. So there is some kind of down voids, and this minus 1 is not exactly minus 1. But it was, I thought it would get a Nobel Prize, but so far no. But the high C measurements prove this model. So that was interesting. So to summarize, the fractal global model for chromatin structure suggested by Gosberg and co-worker were the fractal dimensions are df equals 3, but ds equal dl equal 1. So dl equal 1 because it's one-dimensional, it's a line, no cross-links, and it follows that ds also must be 1. And the fact that df it's been reported in various experiments tells us that probably there is some cross-linking, very weak maybe. And also, in that case, we expect ds larger than 1, dl larger than 1, because it's not yet it's not anymore a manifold in one dimension. And actually, lamin A was suggested by the group of Yuval Garini and the Technion. So they found that, or they suggested, it's not a proof, that if you don't deplete lamin A, you have these crosslinks. So some changes. But we are back now to mathematics. So I applied math. Let's do math. Let's try to do math. So what kind of models of dynamics? So one model that I will use, I mean, the main model I will use here, I will not talk about that, is the Rouse model. So this is the full Langevin dynamics, only the thermal system without active noise. This is the white noise, friction. Gamma is a friction coefficient, which we didn't have before when we looked for vibration. This is the vibrational part, and this is second derivative Newton. So high damping, you throw this. High damping, small size system, you can probably, you know that you can throw inertia and you have this kind of equation, and that's the Rouse model in high damping limit. And just to say, there are other models. It depends on the physics that is around. The Z model takes into account the hydrodynamic interaction, basically the fact that you move something. There is a force on here. This guy moves. It creates a flow field around it, and then it moves this guy. And it's a tensor, actually. It's called the Osing tensor. It's used a lot in polymer physics. But I will not talk about it here today. So I'm just mentioning it, this thing. So how can I tell you more with respect to just to the introduction? It's not yet the work. Is that we solve this dynamics actually, you know, we stepped on the shoulders of other people. We solve these dynamics. I will show you how you can get all the results with scaling. So that's easy. So let's assume the MSD of a certain node inside the fractal scales like that. This is the static MSD and the scaling function of T over the longest time. Now, what you need to conjecture or assume, well, you need to know that the static MSD is behaving this way. As I showed you, this is called the Landau-Pyrez instability that you can actually you can get it from the fact that the density of states is omega to the ds minus 1. So you can calculate it. For some reason, I have the error there I cannot get, but anyhow. And the other thing, you have to conjecture that the longest relaxation time is this static MSD divided by a certain diffusion coefficient, the center of mass diffusion coefficient. And you know that for Rouse model, you have D is going like 1 over M because it's local friction. Each bead feels the local friction. And for Z model, you know it should be like the 1 over RG, the gyration radius, because it's basically, it's like, yeah, that's what you know from polymers. It's moving together. All the beads are kind of moving together, and you feel only gyration radius, and you know how this scales. And if you know how this scales, you know how this tau n scales from here. And then you have to assume that at short times, the bead inside doesn't know about the size of the system because knowledge is time to propagate to the periphery. So you assume you assume no independence for short time, so you get this power law, and let's just leave it with the Rouse model. So you get immediately that the Rouse model will give you an exponent, an anomalous diffusion exponent, 1 minus ds over 2. So we understand, okay, now full equations give you the same thing. So we understand the thermal system. But what about the active network? So here we decided to study two general models of how forces are acting. So forces can be from the cytoplasm, all the cytoskeleton, whatever you have there. There are forces that are propagating into the neural network, and there are external forces. So they are called force monopoles. It's like you have a network and some other people, let's say a network of people, other people from external are pushing you. But you are connected by springs. So these are force monopoles. They can be external. They are external. But there are force dipoles. So these should be an arrow here that you could see. The dipoles are internal forces. So even chromatin has enzymes, helicases, and so on. They are doing some work, and they can, by Newton's third law, they can, if you pull something, you have to pull from the other side. So either let's say I'm some motor, I'm either pulling or pushing. Yeah. If I'm from external, I'm, let's say, pushing, I push too, but I'm external. I don't care. Now I don't care what happens. I'm exterior. So these are the two general forces we pick, and that's how the field of monopoles look like. You get contribution every time you see a certain force. And here you have, it's a pairs, sum over pairs. So every time I have a force here, I have another force here. These are contractile force dipoles, and they can be extensile, whether it's outward. Extensile and contractile. Okay? And that's why now it's with minus sign, because it's opposite direction. And these are internal forces. So if I will go, for example, to the equations of motion with the displacement field, then here I simply have the active force instead of on each node. I might have I might have a force, I might not. If forces are everywhere, then I will have on all nodes, and I have the white noise still. So this is the field, as I said, of force monopoles. And you can write it a little bit different way. And this is the field of the force dipoles. These are the dipoles. Okay, these are the contractile dipoles. And the point is, you have forces, but all the network is connected by springs. So you have a force here, all the others feel that force by the network.
So you're going to solve these numerically, right?
So we solve it analytically.
Analytic.
Yeah, but only for scalar elasticity.
Okay.
And we did a few tricks like.
Well, why the high damp model as opposed to?
Excuse me?
Why are you going with the high damped model?
Because that's your physics. So I can try to do. That's physics because it's small scale, and then I think above 20 microns usually you have to think about. It depends on parameters, but yeah. What physics do you bring to this active noise? We use the random telegraph process. So basically, we say first of all forces are stochastic with this random telegraph. Tau is this correlation time. P is probability for force, 1 minus P probability for no force. And basically the forces on different nodes are uncorrelated, and they can be in different directions. So there is a mean force, that's why you have this term as well. So this is standard, more or less. And so you asked about that. So what do we do? Analytical theory, only the scalar elasticity. Okay. Any question about that? Because I'm moving fast. Right? Everybody knows random telegraph process? That's telegraph. Long time ago. Okay. You have only two parameters, P and tau. Okay, and it's stochastic. So, and this is the autocorrelation function. Okay. You can ask me a question in the middle. So, scalar elasticity. So the trick is first of all to go to normal modes, like you don't know what are the normal modes. You have to solve them. Doesn't matter. It's a network. It has normal modes. We know some properties of these normal modes. So that's how it looks like. And to make it be applicable also to Z model, so I made everything with an index alpha. But for a Rouse model, lambda alpha is just 1 over gamma. So it's not independent of alpha, 1 over the friction. And gamma alpha is therefore m omega alpha square divided by gamma. Omega alphas are the frequency of the normal mode alpha. Okay, we have to solve them in principle. Numerically, we have to solve if we want a numerical answer. The fluctuation dissipation theorem translates in normal mode space to this equation. So there is still KT here, but there is lambda alpha. You need that. But it's still white noise. That's for that guy. And for force monopoles, we now look only the fluctuation above the mean. Okay, there is a mean because it's not from -1 to 1, it's from 0 to some F naught. So there is a mean force, and that, sorry about that. What did I do? I have to go back. No, no, I'm lost. I lost the direction. Yeah. So we are looking at the fluctuation of the force, the active force about the mean. Okay, and so we just use this delta, the delta without writing a delta here, delta of the force field in normal mode space. And we make use of a few properties of the eigenmodes that are true for both for disordered fractals and the deterministic fractals. Disordered fractals, it's like critical percolation clusters. And this is quite terrible, I understand. But this is scaling. So ds over dl is a scaling function that connects distance and frequencies, space r and frequencies. And if you know to know the behavior at low frequencies and just at the shortest length scale, then this is the behavior. Okay, if you don't know enough, but this is again something which has been studied for a long time on percolation clusters maybe. But let's try to move on. Maybe numerical results will be easier to understand. The force monopole in correlation function, the autocorrelation function in the normal mode space looks like that. And for force dipoles, there is some prefactor here depending on frequency. That's what you get. And then you can calculate the MSD. The MSD in D dimensions. And it has a thermal part, which is the same as the thermal part because it's just active plus thermal noise. So there is MSD thermal and MSD active. This is the MSD thermal, and this horrible thing is the MSD active. Again, sorry about that, but you have this tau of correlation function of the correlation time of the noise, and you have gamma alpha, you have all the functions. Now, in fact, you can summarize the bottom line in a few words. So the Rouse model for the MSD shows you that indeed for short times, forces are uncorrelated, the active forces, and you get superdiffusion. Nu is larger than 1, let's not mention now the nu, but for long times, T much larger than tau, forces become uncorrelated, and you do get analytically that both exponents are the same, are equal to 1 minus ds over 2. And actually, it's consistent with studies on polymers, like Gomper and his group. So that explains the subdiffusion of chromosomal loci. Sorry. And for force monopoles, interesting, no anomalous diffusion regime. No anomalous diffusion. Only the force for force dipoles. For force only force monopoles and Rouse model give you this kind of result. In fact, the Z model, which I'm not talking about, doesn't also give you that. So in order to study it numerically, Sadna did a lot of Langevin dynamic simulations, are quite heavy. And so also comparing to analytical theory and things that you cannot get from analytical theory. But not on chromatin, on the simplest fractal that we could think of, Sierpinski gasket. Why do it? Chromatin is not Sierpinski gasket, but we have a general theory for any fractal that we just need to plug in fractal dimensions, spectral dimension, topological dimension, fractal dimension, and we know the result. So we can check this first on Sierpinski. And biologists don't like this attitude. Definitely, we know that. And then we can use the analytical theory for chromatin or other fractals. Okay, that's the idea here. And it's because of you want to make life simple. And again, it's the way you, depends on your attitude, I guess, or your viewpoint. So the Sierpinski gasket is just triangles and triangles. And this is, for example, second generation, third generation. This is ninth generation. It's one of the most known fractals. And I even read a recent paper that people found a molecule that looks like that. I don't know if it's right. A real molecule. So anyhow, so here are the results. So first of all, thermal motion. Now, what we see in short, we have short time superdiffusion. It's not superdiffusion, actually diffusive, sorry. And then this is the regime of the subdiffusion. Just diffusion, very short time diffusion, and regime of subdiffusion. And the exponent here is exactly what you expect from 1 minus ds/2, exactly that. There is a small difference in the amplitude if you take B, the equilibrium distance of a spring, to be 1 or 0, okay, just using dimensional units. But once you take 0, then the analytical theory and the Langevin dynamics give you the same result. And this is for a quite large Sierpinski gasket. Then it goes to center of mass diffusion. Then let's look about the active systems. So, as I said, short times will be superdiffusive. In fact, it's ballistic. Okay, it's because before active forces are decorrelated, simply t squared, and then you get x is going like t, constant velocity, and you get t squared. But then this is the interesting regime for different values of the force strength and correlation time for the force. And as we predicted analytically, we get this kind of active subdiffusion exponent, which is exactly equal to the passive one. Okay, it's exactly equal. But of course, the range of this subdiffusion regime before it goes to T and is depending on parameters. And I have to say we remove the drift. And because there is some drift, because there is some net, it's force monopole. So even if you choose them at random direction, there is some small net force which give you a drift. Remove the drift here, so you get only diffusion. We also predict the ratio of active to passive amplitudes. And the main thing to know is it's going like phi is the concentration of monopoles, not necessarily one. Okay, f squared tau. That's the most important thing. And these are more results on force monopoles. I had t equal to 0 because no active. Now you see what happens if you don't remove the drift. You get t squared, but if you remove the drift, you get t to 3/4. Again, some kind of comparison between b equal to 0 and b equal 1. So we are happy actually with the analytical result. So that brings you to the notion that some people resent of effective temperature. So what we find analytically, there is an effective temperature, which is T plus this kind of ratio of B active to B thermal, the amplitudes. And in fact, it just tells you how much the passive power law is smaller than the active power law. Similar to what was found in experiments on chromatin, the exponents are the same. Okay, let's move on. What about force dipoles? Now, it turns out that analytically you can show that because of this inequality between exponents, 1 minus ds over 2 minus ds over dl, smaller than 0 always, actually, or for almost all fractals. I don't know any fractal it's not, but I don't have a proof. Then instead of having an intermediate subdiffusion regime, you saturate into a constant, then you go up again. So that already tells you that whatever you see, let's say in chromatin, cannot be from the force dipoles, cannot be from internal forces, cannot be. So how do we apply for chromatin? In fact, it's hard to know what's going on in chromatin. It depends also which kind of cells, but you can estimate in dimensionless unit the strength of the forces, the range is wide, and also the range of tau, because these are the range of correlation times of various enzymes and motor proteins. So it's a very wide range. And we take something which has been used in the literature here in these examples, these values, and what we see is the following. We see everything. I mean, we put everything, sorry. So we still have only this red thing is only thermal, only this thing. Otherwise, these triangles are thermal plus monopole plus dipoles, but 40% monopoles, so there is some fraction, 20% dipole. This was this phi. And same strength, same strength. Now, okay, so that's what we have. The thermal, as we know, give us this exponent. What about the triangles? They also give us this exponent. All of them work together, but clearly the dipoles don't contribute to this thing. So you see the dipole saturates here, dipole MSD saturates here, and that's what we predict for the total. So it's mainly as a contribution from thermal and monopole, and both of them are contributing. Probably, as you can see from this curve, the monopoles are stronger. So are more dominating this amplitude or this parent diffusion coefficient. So we say for sure that what they see in experiment is because you have also force monopoles and temperature, of course. But there are other things we found here, not related to chromatin, please.
Is this because the dipoles are asymmetric? Like, is it because you have symmetry breaking in the monopoles compared to the dipoles? Is that it?
I guess so. So from my point of view, it's a good question because I don't have so much intuition. It's because of this inequality. Okay. But you can see that even if ds is 1, which is a line, and dl is 1. So this is the pure fractal global model, okay? So 1 minus 1/2 is 1/2, minus 1 is minus 1/2. So it's true that you could, but not, people didn't say that before. So people didn't say that. Actually, people only talked about force dipoles as everybody knows it's couples to the extracellular, to the cytoskeleton. So I think this is the new thing here is to say, at least on fractals, force dipoles will not give you this kind of subdiffusion. But of course, there is something. There's an effect, but it doesn't. So where I'm going? No. Okay, so what about the other things, if I have some time? Because the other things might be very interesting for other people. Maybe it once. So, for example, we found that this thing can rotate only for force dipoles. So force dipoles don't give you a net force on the object, so it will not give you translational motion, of course. But normally, for a rigid body, it shouldn't give you any rotation because each dipole it puts a net torque on the center of mass. So if it was a rigid body, the total torque is zero, no rotations. Can't be. But in fact, what we found that the MSD, if you have, let's say, 20% force dipoles, the MSD starts to do these things. And then it oscillates further. While if you have full force dipoles, you don't have this. So how can it be? So it's actually experts in deformable bodies that we were not. Talked about this kind of crawling motion of nano swimmers, nano objects. So the net torque, zero torques, tells you this equality, but this can be non-zero. This can be non-zero, and in fact, but you have to somehow break the symmetry, because if you put dipoles everywhere, you don't see that. Okay, here it's a flat line. You see, it's a flat line. It just saturates 100% dipoles. What's the explanation? Well, we don't know the explanation. Well, we know, I mean, the simulations know the explanation, and people, experts in deformable bodies know that. But what you have, although all these angular velocities fluctuate between different beads, if you look at long times, depending on your distribution, you don't have a full fractal with all dipoles everywhere, you get some residual or long time crawling, we call it crawling rotation, either right or left, depending on the distribution. That's a movie, so the movie doesn't cheat. And also, it's actually going down with the size of the system. So it's going down when you have dipoles everywhere, but it's going down also with the size of the system because it's related to some imperfect anisotropy, okay? So you see, and the direction. So in fact, there are lots of papers on what is called just triangular microswimmers. They put three dipoles, but they decide their strengths in this way, either clockwise or anti-clockwise inequalities, sorry. It's called nanoswimmers, microswimmers, triangular microswimmers. It's a field. And we have, all dipoles are the same, but we are distributing them. And only when there are dipoles everywhere, we can say there's no this kind of effective inequality clockwise. I don't know if you can call it chiral symmetry breaking or not, I'm not sure, but anisotropy, yes. So to make long story short, I have to finish, right, very soon. And I'm not doing it the right way. Okay, so this, for example, here you can see that angular velocity, sign, and magnitude depends on realization of force dipole distribution. So it's not the same. These oscillations in MSD come from this rotation. It depends, of course, on force strength, and angular velocity diminishes with increasing system size, which is diminishing symmetry breaking of standard deviation. So for infinite system size, then it's not gonna be there. Another interesting thing is a collapse. And then I finish by that. So I'm on time by 2 minutes, or maybe. So this was for low or medium forces, but above a certain force strength in our units now it's 1, you have a collapse only for force dipoles, okay? The network collapses on itself, okay? And that's what you get for the gyration radius, you see that. If these are contractile dipoles, it goes inside. If it's extensile, also go inside, but then goes up again for higher forces. And is this a real phase transition? Yes, it is. Because if you increase the system size, you see how this transition, the collapse of the network because of active forces is sharper. Also depends on parameters. If we want to justify it or to explain this, we use a hand-wavy argument. This is called persistent length. For some reason, they borrowed it from, in the field of active system, they borrowed it from polymers. So a free particle persistent length is just F0 tau divided by gamma. just the position after time tau. It goes with the constant velocity. In a harmonic potential, it's this. So this is the distance a particle travels under force F0 up to time tau. And now we only say the following. Let's equate this with B, the equilibrium distance of the springs. That's the idea, actually, not the general idea, but we apply it here. And then you get a critical force for collapse. And in fact, it works just well with that's the hand-waving argument, but that's what they do in active system dynamics, and it works here too, okay? And not more than that. I won't say more than that. It's probably should be studied more. So let's just summarize the following. Active force monopoles under Rouse model in fractal model of chromatin are consistent with experimental anomalous diffusion in bacteria and yeast cells of both passive ATP depleted cells and active normal cells. Subdiffusion exponents, nu active equal nu thermal is equal to 1 minus ds over 2, suggests that ds is 1.2, implying some cross-linking, e.g. lamin A. That's the immediate, what comes immediately to mind. Force dipoles do not induce anomalous subdiffusion. They can be there, but they are not those responsible for this observation. Force dipoles can induce crawling rotational motion despite the Weshing torque. This was not seen in chromatin, and I don't know other systems. In fact, I don't know why. Although the cytoskeleton is known in mammalian cells to make some turns, so it might be related to that. And force dipoles can induce network collapse above a critical force magnitude, signifying a true first-order dynamic phase transition. And thank you for your attention and having me here in the Israeli Independence Day.
We have time for a couple of questions.
In the chromatin system, what is responsible for, like, what would be responsible for, like, the force dipole or the force monopole?
So, yeah, so there are enzymes in chromatin that are responsible to unwind and open, okay, and helicases and so on. So they are motor proteins, in fact. Force monopoles, it's mainly the motor proteins in the cytoplasm. So, and that's why actually always when people looked at motion of some probe particle, Dave Waits did a lot, and with Michael Elbaum we did also, and it wasn't just thermal motion. Sometimes the exponent would look like Brownian motion, but the diffusion coefficient is way up. So basically that's it's motor proteins. I mean, enzyme motor proteins is very similar. And the truth is that we don't go into it. We just assume there is something. So it's, these terms, it's phenomenological. But our predictions can be tested on artificial systems. I mean,
would there be any way to, because I mean, you're kind of making a bit of a prediction here about like the dominance of like monopole forcing over dipole forcing. Is there some experiment you could do to try to
stop? You could try to stop. No, selectively. This is. I'm not a molecular biologist. Some of them know to do things. Basically, you don't want to stop anything in the chromatin, but you want to stop the cytoskeleton somehow. And I know it's anything like that is a nightmare, but they can stop selectively certain proteins, like they inhibit dynein, they can inhibit kinesin, they can inhibit myosin. And maybe they should use all these drugs to inhibit all motors, and I don't know what it does to the chromatin enzymes. So I'm a fake biologist. Yeah, that's the truth.
Other questions? So let's thank our speaker again, and Ronnie, stay on the hold. Got more questions.
Yeah.